Recall that with our non-standard models of weak S1S, we had some sort of agreement phenomenon. Suppose that we had a model that had the following word in it, where again we can understand words to represent, for instance, characteristic functions of sets showing up. So in positions where there's a 1, that corresponds to an element of the set, and in positions where there's a 0, that corresponds to an element not in the set. So if we have a set in our model, a word in our model that looks like this, we can modify it in finitely many places. Our sets in our models are closed under finite modification. So for instance, we could modify our original set in a few places and wind up with a set that looks like this, where the key thing is that at some point, if we're looking at the interior of this thing, everything agrees. This is equivalent to saying that we've only made finitely many modifications, right? If we make a finite number of modifications, there's going to be a largest point where we have modifications on this half, and a smallest point where we have modifications on this half. And on the interior of that, on the infinite middle bit, we're going to have the same behavior of these two sets. And in particular, we must have agreement. While we know that our non-standard models necessarily have to have one of these two sets in them, it can't have both. Specifically, since our non-standard models are closed under certain types of operations, we can take the symmetric difference between these two sets. We can take the set of positions where they disagree, and that gives us a set that looks like this, and this set doesn't have a smallest element, contradicting what it means to be a non-standard model of weak S1S. Another way of looking at this exclusivity is that once we know the behavior of the set going into the infinite bit, then we know the behavior of the set coming out of the infinite bit. Now, admittedly, at any point coming out of the infinite bit, we can start having arbitrary random behavior. But that happens at some distinct point, and there's infinitely many positions before that distinct point. This exclusivity phenomenon also works the other way. If we have two sets that agree going backwards into the infinite bit, then they also have to agree coming backwards out of the infinite bit. Again, up to a certain point, at which point it can start having arbitrary random behavior. In this video, I'd like to show you how we can formalize this notion of if two sets agree going into the infinite bit, then they agree coming out of the infinite bit. But there's still the possibility for like arbitrary behavior on these finite bits. And to generalize this phenomenon to the case where, so these sets here are, elements of really basic non-standard model whose first order part looks like omega followed by a copy of z. But what about more complicated first order parts? Do we get a similar exclusivity phenomenon going on in the infinite gaps? Well, the answer is yes, and I will show you what that looks like. So to start off with, it's even challenging to try to describe the location where this sort of infinite phenomenon is happening. So a cut on a linear ordering, and when I talk about linear orderings here, you should be thinking about woozles, but if I say a linear ordering, then this stuff works for arbitrary linear orderings. It's going to be a partition. We're going to divide our linear ordering into two parts, two different sets. They're disjoint and their union is the whole thing, where all elements of the lower set A are going to be less than all elements of the larger set B. So essentially, we're just dividing our linear ordering into two parts. Everything on one side of the line is part of our left set A, and everything on the right side of the line is part of our right set B. But of course, we're not interested in this position here. Nothing interesting happens here, right? Our sets can have arbitrary behavior over here and arbitrary behavior over here, and there's no agreement, there's no determining, there's none of that stuff. So we want to focus specifically on infinite cuts. And we'll say that a cut is infinite if the left-hand side has no largest element and the right-hand side has no smallest element. So specifically, if we're looking at omega plus z, this is the cut that we're looking at. And specifically, when we're thinking about arbitrary woozles, an infinite cut is anywhere where we're not cutting through either an omega part or one of the z parts. We're cutting kind of between them. I'll say that two subsets of our linear ordering, again, we should be thinking about these as second order elements in our models, but this works in general. We'll say that they are tail equivalent over a particular cut, AB, if they agree on elements of A beyond a certain point. So imagine that we have our linear ordering here. We have a cut that divides the world into two parts, A, the left-hand part, and B, the right-hand part. And then it should be the case that there's some point within A where these two sets agree on the remainder of A. They don't have to agree on B, and they don't have to agree on the initial part of A. They just have to agree on this bit here. Right? So thinking back to our original example, where we had some arbitrary behavior, but then eventually we started to agree with this other set here, and then we had to do some agreement over here. That's what's happening over here, right? We're leaving room for some arbitrary behavior over here, but eventually on the rest of A, these two sets have to agree. Eventually, these two sets have to agree. And of course, we're going to want a similar notion on the other side of things. We'll say that two sets are head equivalent over a cut if they agree on elements of B before a certain point. So there's going to be some point in B where they have to agree on this interval here. They don't have to agree on A, and they don't have to agree on the remainder of B, just this bit here. And with this, we have the language to describe our agreement phenomenon. If we have two sets that are tail equivalent over this cut here, that is, that beyond a certain point they start agreeing, then it necessarily is the case that they have to be head equivalent over that cut as well. It needs to be the case that up to a certain concrete point, the two sets agree with each other, and then beyond that point, they don't have to agree. They can have arbitrary behavior. Contrast that, on the other hand, with these middle two sets. These middle two sets are tail equivalent. There's some point beyond which they agree, and in fact that point's pretty early, but they're not head equivalent, right? There's no matter how far, how early we go over here in this z part, we're not going to find a position where these two sets agree entirely on this range here. So these two sets are mutually exclusive with each other because they're tail equivalent but not head equivalent. And similarly, these two sets, these last two sets, are head equivalent, but they're not tail equivalent. So they're also exclusive with each other. So specifically, if we have two second-order elements in some non-standard model of weak S1S, of course this bit here does not apply to arbitrary subsets of linear orderings. If we have two second-order elements in some non-standard model and an infinite cut on the first-order part of that model, then these two sets have to be tail equivalent if and only if they are head equivalent with each other. Tail equivalence and head equivalence are fairly strange phenomena in the sense that I can take a set or a word and change it in an arbitrary position. I could even change it in position like 100 or 1,000 way out here and not change the tail equivalence class or the head equivalence class. I can change any one of these digits, any one of these, whether or not that element is in the set or not in the set, and still have the same equivalence class, as long as I only change finitely many positions. Because at some point we'll have the furthest out change that we've made, and beyond that it's exactly the same set. Put another way, telling you about the digit in the hundredths place, that is whether or not 100 is included in this set, it doesn't tell you anything about its tail equivalence class. And telling you about the tail equivalence class doesn't tell you anything about the digit in the hundredths place, because again we have things that are tail equivalent to each other that are different in the hundredths place. Getting used to this sort of notion of equivalence is very similar to getting used to the oddities of limits in calculus. When I say that the limit as x approaches 0 of f of x is, let's say, 3, that doesn't tell you anything about f of 0, and it doesn't tell you anything about f of 1 or f of 1/100th or f of 1/1000th or anything. It doesn't tell you any specific values of the function. And yet, nonetheless, it's capturing some information about the function. Similarly, the tail equivalence class and the head equivalence class don't tell you anything about what's going on at specific positions, but rather tell you what's going on kind of around a hole. And of course, if you're going to study these sorts of things, you want to be able to say, oh, I'm interested in the set of all things that are tail equivalent to this collection here. But abstractly, what that means is taking our equivalence classes and picking out a representative element from each of them, which is a use of the axiom of choice. So if you want to work with these sorts of equivalence classes, you really do need to make essential use of the axiom of choice. So some counterintuitive things might wind up happening. Another way of phrasing this fact is that within a particular non-standard model, the tail equivalence class of a second-order element determines its head equivalence class, and vice versa. This gives us some sort of matching. We have a bunch of different tail equivalence classes that correspond to very specific head equivalence classes. What this winds up looking like is a bijection between the tail equivalence classes and the head equivalence classes. And I want to call this bijection, I want to call this function the tail-head map for this particular cut. Of course, different cuts will have different tail-head maps, and if we look at different non-standard models, they might have different tail-head maps as well. It's worth noting that this isn't quite a function. If you really wanted this to be a function, then it should be the case that all tail equivalence classes get mapped to some head equivalence class. But we've seen that doesn't really happen. If we're looking at, let's say, the most basic thing we could be looking at, where our woozle is omega plus z, and the second order elements of our model are just the piecewise periodic sets on this linear ordering, then the sorts of tail behaviors that we can have necessarily have to be periodic. But of course, there's a bunch of behaviors that we could have here that aren't periodic, right? It could be the case that we're looking at, I don't know, the digits of pi in binary, or there's a 1 just in positions that are given by prime numbers or Fibonacci numbers or whatever. Those can't be part of piecewise periodic sets, and so they're not part of this model. And so those tail equivalence classes don't get represented. So not every tail equivalence class, not every end behavior for a sequence is necessarily going to be represented. And similarly, not every head equivalence class is going to get represented. But the tail equivalence classes that do get represented are matched up 1-to-1 with the head equivalence classes that get represented. So it's still useful to think of this as a function, just a function on just the tail equivalence classes that actually wind up showing up. I want to take a moment to look at another specific example. Let's take the tail-head equivalence classes If we have some sort of woozle, then there's an infinite cut on that woozle where we just put the entire linear ordering on the left-hand side and nothing on the right-hand side, right? We make our cut here. And so, of course, the head equivalence classes that show up, well, there's just one, which is nothing's happening. And that's the only head equivalence class that we get on this side. And also the tail equivalence classes are also nothing's happening. Because if we're looking at second order elements of this structure or any non-standard model of weak S1S, there's going to be some point beyond which the second order element doesn't have any elements. And so we could take that as the point that beyond which we're looking. We're talking about this tail equivalence class, and well, there's nothing in there, right? This element here is eventually all zeros. Eventually nothing's in there. And so this function consists of, it has one input and one output. The input is the tail equivalence class, nothing's happening, and the output is the head equivalence class, nothing's happening. There's another really important notion of equivalence for infinite sequences or subsets of an infinite set, and that's equivalence mod finite. So we say that two sets are equivalent mod finite if their symmetric difference, if the set of all positions where they disagree, if the set of all values that they disagree on is finite. And we use the notation x is equal to with a star y to indicate that. This shows up all the time within mathematics, and it's similarly hard to get a handle on like tail equivalence or head equivalence are. We can, of course, change a set in finitely many positions and not change its mod finite equivalence class, kind of by construction, by definition. And as such, telling you whether or not a particular element is in a set doesn't tell you anything about its mod finite equivalence class, and telling you about its mod finite equivalence class doesn't tell you whether a particular element is in the set or not. And again, in order to get a really good handle on this notion of equivalence, you really need to pick out a member of each equivalence class, which requires the axiom of choice. It turns out that equivalence mod finite and our tail-head notions of equivalence are equivalent to each other. To put it more formally, if we have two subsets of a linear ordering, and they agree on all tail and head equivalence classes over every infinite cut, then they agree mod finite, and this is an exact equivalence. If they agree mod finite, then they are tail and head equivalent over every infinite cut. In some sense, what this is saying is that our linear ordering L really consists of two separate parts. We have the finite bits, and we have the infinite cuts. And if we have two sets that agree on the infinite cuts, then the only place where they could disagree is on the finite bits, where they disagree mod finite. But it's slightly more than that. Imagine that we're working over a more complicated woozle for our base linear ordering. Imagine that this is omega followed by one copy of z for every integer. The infinite cuts that we get for this linear ordering, well, there's one between the omega and the z part, and then there's one between every z part. Right, so there will be infinitely many going off in both directions because there are infinitely many z parts going off in both directions. To say that our sets x and y agree on tail and head equivalence over each of these infinite cuts means that there's some interval here over which they agree, and over here where they agree, and over here where they agree. Everywhere we have an infinite cut, there's some interval where these two sets agree with each other. And so there's only going to be these spaces in between where they could possibly disagree with each other. And of course, because these are copies of the integers, these intervals are going to go kind of into the integers some amount, and what's going to be left over is only some finite sequence of integer positions where they could possibly disagree. But you might say, hold on, there's infinitely many z parts. So we could have our two sets disagreeing somewhere in this z part, and somewhere in this z part, and somewhere in this z part, and somewhere in each of the z parts. And in that case, they wouldn't agree mod finite. They'd be different from each other in infinitely many positions. But we've forgotten two of the most important infinite cuts, specifically this one here. And in order for our sets to agree on tail and head equivalence over this cut here, this cut that separates the omega part from all of the non-standard parts, well, the interval where they agree is going to extend some amount into the omega part, and so it's going to go to some concrete number within the omega part, and it's going to extend some amount into the non-standard part. And what that's going to do is it's going to actually cover up to a certain specific concrete non-standard part. And when it does that, because our sets have to agree on this bit here, they can only start disagreeing on some concrete non-standard z part. So instead of being able to disagree on this part and then the one before it, and then the one before it, and then the one before it, and so on and so forth, there has to be some point where, as we're going backwards, they stop disagreeing entirely on all of the z parts. Because that's really the only thing that can happen when we expand out an interval from this cut. And then similarly, we also have the cut at the very end. And well, we know what happens with this cut at the very end in our non-standard models, which is that we're requiring our sets, our two sets that agree on their tail and head equivalence class, to agree backwards up to a certain point. And that backwards is going to go to some concrete z part, maybe the z part for, I don't know, C3 or C2 or something like that. And so beyond that, these two sets can't disagree at all, because we said that they agreed on this entire interval. So on none of these z parts here can these two sets disagree. So there really are only finitely many z parts, and there are only finitely many points within each of those z parts where these two sets are able to disagree with each other. So I like to view this fact as saying if we try to cover all of our infinite cuts, then we wind up covering pretty much all of our entire linear ordering except for maybe finitely many points. So let's prove this fact. First of all, suppose that our two sets agree mod finite. Then I want to show that they are equivalent to each other over tail and head equivalent over each infinite cut. And that's fairly straightforward. If we change our sets in one position, we can kind of move where we're considering our infinite cuts so as this one change that we're making doesn't affect the tail and head equivalence. And of course, if two sets disagree only at finitely many positions, we can go from one to the other by a finite series of single point modifications. For the reverse direction, I'm going to want to prove this by contrapositive. Suppose that x and y are not equivalent mod finite. That is to say that they disagree at infinitely many points z. Their symmetric difference is the set z. This is an infinite set, and an important fact about infinite linear orderings is that every infinite linear ordering has an infinite increasing sequence or an infinite decreasing sequence within it. And of course, this makes use of the axiom of choice. Let's assume the proof is the same either way. Let's assume that we have an infinite increasing sequence within the points z. An infinite increasing sequence of points where x and y disagree. And let's plot these points out. This infinite increasing sequence of points will actually, we can kind of fill it out to get a cut of our linear ordering. And not just any cut, an infinite cut. We'll let A be the set of all points in our linear ordering where the sequence eventually goes past that point. and we'll let B be the set of all points in our linear ordering where the sequence does not go past that point. And of course, it doesn't really make sense to say that there's a point where the sequence stops, because this is an infinite, strictly increasing sequence of points in our linear ordering. So there's no point here separating A from B. This is genuinely an infinite cut. And I claim that our sets x and y are not tail equivalent over this cut. Because if we draw any interval here within A, no matter how far we push that interval, if we draw an interval here, there's always going to be some elements of z that wind up in that interval. There's always going to be some points where x and y disagree. That is to say that there isn't some sort of interval like this where x and y agree. So x and y are not tail equivalent over this infinite cut. And that's what we were trying to prove. So what this theorem is saying is that if we want to understand a particular second-order element of our non-standard models, or just an arbitrary subset of an arbitrary linear ordering, for the most part, we really just have to understand its tail and head equivalence classes over every infinite cut. And this theorem actually gets even better if we're interested in studying non-standard models of weak S1s, because we know that non-standard models are closed under finite modification. So in order to understand non-standard models of weak S1s, we literally only have to understand their tail and head equivalence classes over infinite cuts, and then every member of the mod finite equivalence class of the sets that have to show up because of that must show up, because we're closed under finite modification. So to state this formally, and I like to call this the tail-head lemma, the tail-head functions of a non-standard model of weak S1s, and we require that these two non-standard models have the same first-order part, the same woozle, let's say that's L, then these two non-standard models are the same model, right? This information is enough to determine precisely what model we're looking at. And the proof is as follows. Suppose that we have two different models that have the same tail-head functions and the same first-order part, but they disagree somewhere on their second-order part. And we have some subset of L, we'll call it X, which is a second-order element in M1, but is not a second-order element in M2. This is what we would expect to happen if this fact wasn't true, that we'd have two models that disagreed on at least one element. Of course, it's perfectly fine for non-standard models of weak S1s over a particular woozle to disagree on what subsets of that woozle are in there as second-order elements. Even in the case where we were focusing on just the piecewise periodic models, depending on how we chose the modular remainders for our non-standard elements, we could wind up with models that had very distinct notions of periodicity going up to non-standard parts. These models may have had the same first-order parts, but they would disagree on exactly what you meant by the periodic of period 2 alternating 0, 1, 0, 1 set up to a certain non-standard point. But of course, those models that disagreed with each other had different tail-head functions. And my claim is that if we have two models that have the same tail-head functions, then they're necessarily going to have to agree on all of their second-order elements. So again, suppose that this doesn't happen. Let's construct the following set. Now, our closure properties for non-standard models give us really no hope that this set is necessarily going to be a second-order element in either of our structures. But that's okay. We're not interested in that. We're interested in producing a set that defines an infinite cut. So we'll have it be the set of all z in our linear ordering such that if we look at x up to z, so from the start up to z, then that restriction of x is still in M2. So maybe not all of x is in M2, but maybe some initial part of x is in M2. Somehow if we cut x off at a certain point, that resulting set is going to be in M2. This set here is of course non-empty. If we let z be, let's say, 2, then a set that agrees with x in terms of whether it contains 0, 1, and 2, well, of course, we can produce a set that looks like that, and it's certainly going to be in M2. We simply look at which of 0, 1, and 2 are actually in x, and then we just take those elements and have a set, which is just those elements. And it's going to be a finite set, and of course, all finite subsets of L are in all of our non-standard models, so that's going to wind up being in M2. So this is a non-empty set, and it takes a little bit of figuring, but because M2 has to be closed under finite modifications, this actually has to be an infinite cut. We can't have this set stop off at some z and not also contain z plus 1. If the interval from 0 to z intersected with x is in M2, then the interval from 0 to z plus 1 intersected with x also has to be in M2. Because maybe that intersection has to be the same. If x doesn't contain z plus 1, then these two intersections are the same, and so if this is in M2, then of course this is in M2. On the other hand, if x does contain z plus 1, well, this set here is just this set here unioned with the singleton z plus 1. And because M2, being a non-standard model of weak S1s, has to be closed under finite modifications, this new set also has to be in M2. So this collection of z's that wind up making this work can't have z and not have z plus 1 in it. In other words, this set is the left-hand side of an infinite cut. Technically, you also have to show that A is an initial interval of L, but that's fairly easy to show. So we have an infinite cut. A is non-empty. B also has to be non-empty because at some point, these things stop being in M2. Right? If the interval from 0 to the largest element of x intersected with x was in M2, then that's x. That would have to be in M2. So our cut cuts before the largest element of x. And that largest element of x has to be in B. Well, this is an infinite cut. And so, because our two models agree on their tail-head functions, it may not be the case that x is in M2, but there has to be a set that agrees on its tail and head equivalence classes over this cut with x. Because x was in M1, it had some tail and head equivalence classes. Those show up matched with each other in the tail-head functions for M1. So they have to show up in the tail-head functions for that infinite cut over M2. So let's let y have those equivalence classes. Let's let y be the thing that's showing up in the tail-head function. So specifically, what does it mean for this set to be tail-head equivalent to this set? Well, that means that there's some interval bridging this cut. Specifically, the interval from A to B, where A is in the left-hand side of the cut and B is on the right-hand side of the cut, where x intersected with that interval is equal to y intersected with that interval. Now, of course, these intervals have to be in our non-standard models. Our non-standard models have all the intervals that we could want them to, and they're closed under intersection. So because y is in M2, y intersected with AB has to be in M2, and therefore x intersected with AB, because it's equal, has to be in M2. Of course, because A was in A, that means that by construction, the interval from 0 to A intersected with x has to be in M2. And because M2 is closed under unions, the union of these two has to be in M2. Well, what is the union of these two? The union of these two is x intersected with the union of the interval from 0 to a and the interval from a to b. That is the interval from 0 to b. Contradicting our assertion that b was in b. That is, it wasn't in a. That is, that the interval from 0 to b intersected with x was not in M2. So we have our contradiction. So our assumption that we could come up with these separate non-standard models in the first place was wrong. If we have two non-standard models over the same first-order part, their tailhead functions determine the entire model. Another way of saying this is that if we want to study non-standard models of weak S1s, really all we need to do is study tailhead functions. And maybe there are limitations on how we can combine tailhead functions together. Maybe, for instance, let's say that we have some sort of omega plus z model, omega plus z times 2 model. This has 3 infinite cuts, here, here, and well, of course the trivial one here that we don't really care about because it doesn't tell us anything. When we look at the tailhead function, it just contains the trivial thing. But it may be the case that the tailhead function over this cut and the tailhead function over this cut interact with each other. But that winds up not being true, and in the next video I'll talk about why. It really is the case that if you want to study these non-standard models of weak S1s, the only thing you have to study are tailhead functions. In the previous video, I talked about what sorts of tails we could wind up having over here on the omega part of our models, but that wasn't fully the thing that we were interested in. We're interested in tailhead functions. We're interested in not just what tails can show up, but what heads can get matched to them over these sorts of infinite cuts. And of course, we could also be interested in studying more complicated infinite cuts, like the one we saw where we had one z part for every integer, or ones where we have one z part for every real number or for every rational number. Those get a lot more complicated. But let's focus on kind of the simplest question. Let's say that we have an omega plus z model. Ignore this bit for now. What sorts of tailhead functions can we have over that one infinite cut that we wind up getting in those models? And I'll make a video talking about that as well. And that should hopefully wrap up all of the results from my thesis that I want to present, and then we can move on to some other interesting topics. So please let me know if you have any questions in the comments down below, and I hope to see you in a future video.